All right, welcome. So in the last video, I introduced the popular NEAT algorithm for evolving the topology and weights of a neural network. And I want to show it in action in a simulation that was created by my students. So let's take a look. So because I'm interested in artificial life tasks, I started with a common task that I start with in most of my simulations, which is foraging, which is just going out, finding and eating food. So the agents in our environment, they're gonna, drive around and they're gonna interact with these little pellets of food that just exist there. If they collide with them, then we say they ate that food. And so they have a little bit of energy, and if they run out of energy, they just sort of stop where they are and die. But if they can eat food before they run out of energy, then that can top them off. And then if they can get in, a pattern of doing that, they might be able to eat a couple pieces of food before they run out of time at the end of each generation. If they do end up eating the initial food that's in the environment, in this example I have 3 pieces of food in the environment, but we can set it up in different settings. Then whenever food is eaten, it's usually respawn, just so that to encourage them to eat as many pieces of food as they can in the time that's allotted to them. So this is a fairly simple task and a pretty common task that you might assign to some evolutionary robots. So our robots, as you can kind of see in our visual depiction here, are going to use simple kind of laser-based or ray-casted based sensors. So they're going to, from a single point on, as you can see here, there's sort of one eye on the front of each of our agents. And from that point, they cast out 13 different rays, and they see the first object that it interacts with or it collides with. And in our case, we will be sending back 2 pieces of information from that ray. We're both going to send the distance from that collision, so sort of traditional obstacle or object detection. And then to give our agents a little bit more information about what they're seeing, we're also going to give them a second piece of information for each of these rays, which is going to be the color of the object that they see. And for our neural networks, we have basically decided for the robot, what the robot sees is the colors orange and pink, while we see, a green piece of food and maybe a black wall. When the ray interacts with the wall, which is dangerous to our agents, it sends back an orange signal. So that's the signal to it, to our robots, that this is a dangerous signal. And then when it interacts with food, it will send back a pink signal, which is the signal to our agents that it is something you want to chase down and eat. And so this particular signaling was selected because these 2 hues in the hue space are going to be, even though they look close together for our eyes, and they actually are close together, the way they're represented numerically, one of these is close to 0 and one of them is close to the maximum value, and after we normalize it, that means close to 1. And so for our agents, our robots, what they're basically seeing is that color neuron, when it's interacting with a wall, it's not firing back any positive value at all. It's probably at value 0. And then when it interacts with food, it sends back a 1. So that one neuron for each of the rays, there's 13 rays, that one neuron for each of the rays will be 0 if we see something dangerous, and 1 if we see something we want to seek out. And that's by design. So again, we've just selected those particular colors for feedback from the environment that our neural net will hopefully be able to adapt around. So because of these 2 signals per ray, and we have 13 rays, of course that results in 26 input neurons, the standard inputs. We also have a small collection of other inputs that we have experimented with at times. There's one that we typically leave on, which is just always wired to 1. So if we want to have some input coming from somewhere, we have one that's always tied to 1. And then we also feed their energy value back in as a neuron input, and we've also experimented with feeding their wheel outputs back in as inputs, and so on, so that whatever their wheels were at last turn, we might feed that back in. These are all pieces of information that the neural networks might want to use to change their behavior, and so we've experimented with that. But the general sensor structure are these 13 rays with their 2 inputs each. And then the output, we have a pretty straightforward output. We have experimented with a few other outputs, but we've really just stuck with two for most of our typical runs, which is just the two wheels. And so we have a 26 to about 20, maybe about 30 inputs coming in, and we have two outputs coming out of our network. And we begin our networks with an initial structure of just those neurons that I've just described, but fully connected so that all of the input neurons are connected to both of our two output wheels. The neurons in our neural networks are pretty straightforward. We could have used a different activation function because there are a handful of different options that you might want to pick out. I've used the sigmoid function just because I've used that in a lot of my other experiments and I have a little bit more familiarity with it. Not because I think it necessarily would be the best one for this experiment. Maybe there would be a better one, and that would be something we might want to look into in the future. But because we have explored this one before and we are a little bit familiar with some of its parameters, two of the parameters that are important in the sigmoid function are the k parameter and the m parameter. The m parameter will move the function sort of back and forth here. So we might move that center point. This one's aligned at 0 in our diagram, but we could move it out to 1 or 100 or wherever we want to move it by changing this m value. And then the k value changes the slopiness. So how steep or how shallow is that slope? And in our simulation, we thought, hey, it might be, we weren't really sure what value in particular of k that we wanted to put down. And we also really weren't sure about m, and we had just defaulted that one to 0. But k was the first one that came to mind because the slopiness actually, especially in the output neurons, affect how fast the wheels go. So because if we have a really steep slope here, then that means the output of our neuron is almost always going to be either -1 or 1. And that may make it hard to drive if those were the only two speeds you can have is full forward or full backwards. And we weren't sure how steep we should make it. And after going around and discussing it a number of times, we thought, well, why don't we just let the neurons decide? Because again, evolution is a pretty powerful tool. And so we added to the NEAT algorithm. This is just a small adjustment where we decided, in addition to adjusting the weights, which is a normal thing we would do, we would also adjust the k and the m values in our neurons so that they might find good values so we don't have to do it ourselves. We use a pretty straightforward and simple fitness function. One of the things you do a lot when you are experimenting with evolutionary algorithms is, especially if you have a fitness function, is you're going to adjust some of its parameters, the weights, the relative weights. I'm not going to go into the details of what weights I'm using in the current settings because as we found in our own experimentation, the weights do definitely impact it, but we've sort of found a small sweet spot that we like. And the fitness function works in a very straightforward way. We've experimented with adding other components to it, but the two components that have been the most useful for generating the behaviors that we like are rewarding our agents for how much food that they eat in a particular run or generation, and then penalizing them for how long they spend dead. And that's sort of a more general term because they can die in two ways, either just by not eating enough food, and running out of energy, or by running into one of the walls, which is more common later on because once they learn a little bit how to get food, they usually can maintain their energy levels. It then becomes on how much food that can they find, but avoiding the walls is sort of an ongoing problem that they have to learn to do. So we sort of lump those two together into just being dead, and we penalize them for how long they spend, how many ticks they spend being dead. And we've adjusted the weights on these, as I mentioned, in some of our experiments to see if how much this affects our agents' abilities to evolve interesting behaviors. I kind of hinted that we're using a specific epoch every generation that we are going to allow our agents to run for a certain number of ticks. During that time, they're allowed to eat as many, or try and find as many pieces of food as possible, contributing to their fitness, of course. But then we cut them off at 700 time steps. We picked 700 time steps kind of arbitrarily. Truthfully, we started with 1,000, and we were just waiting too long for our evolution. And we said, okay, let's see if we can. We moved it down to 700 to appease our own eagerness in that situation. So that's where we got to 700. And of course, sometimes in our testing, we might reduce that even more, but that starts limiting their ability to actually eat the food and perform the task that we put them to. Okay, so what I have here is an example of our simulation. This is our simulation running, and as you can see, I've started us out here with generation 223. So I started out with a simulation that's been running for a while. I've had it running for a while in the background. And you can see that our agent here, the one that we're focused on at least, we release each of them in their own world. You can see on the right hand side there's a whole bunch of them going around trying to find food. But at least for this agent, it was able to find some of the food. Well, this one looks like it ran out of energy now. But let's look at this next agent again. At this generation, most of our species are pretty good at quite rapidly seeking out some food and finding it. This one almost looks like it's maybe being played by a human controller playing a video game, quite rapidly just going out there eating the food. And this is showing a highly adapted neural network already that's sort of learned the task that we asked it to. You'll notice they don't, oh, well, let's check this out. Oh, see, so I was curious. It was very close to the edge. Was the robot going to be able to avoid? Here's another one. Let's see. Ooh, very good skills, very good dexterity for the robot to go scoop the food that's near the edge. Early on in earlier generations, that's sort of a challenging task for them. Finding the food can be kind of an easier thing to do, but then finding it and not crashing into the wall after is a little bit harder task. So what we can see here is that after many generations, our agent has been able to adapt to the task that we had. All right, now let's take a look at an example of one of our agents earlier on in the simulation. So this is generation 1 or 2. We usually start out at generation 0. So this is only a few possibilities for mutations. And we can see that the standard kind of behavior for these agents at these early generations is, well, maybe we just spin around. And that's not really good. We can check out maybe a couple of our agents. Let me see when we start our new generation here. Some of them are actually moving. Oh, unfortunately, that one was driving backwards. When you're driving backwards, your chance of crashing into the wall is pretty high. But moving around actually allowed that one to scoop up some food. Okay, here's one that's driving forwards. But again, early on, wasn't sure if it should eat the food or crash into the wall. So early on. So what's happening though is some of these agents are actually going to be rewarded if you just accidentally go scoop up some food. So just moving around is in these early stages usually going to be a beneficial thing to do versus some of our agents that just do the old spinorama, and spinorama isn't going to get you anywhere. So over a while we should expect the spinorama agents to be weeded out of the population. Let's check out. So this one just died. Okay, here we have one finally driving forward. Okay, not sure what to do with the information it's getting from its lasers yet. Okay, you might think of these agents as being like young agents. We're evolving them so they actually, we make a new one, but you can think of them sort of learning what their sensors are meaning. So this one sees the food and is really not sure what to do, and it's kind of stuck in a loop here. It's getting a strong signal from that food, and it's just, if it can just wire that up in a future evolution, a future generation, to get it to respond properly to that food and drive into it, then all of a sudden we're going to have a really successful species. So this is about 7 generations in. Now let's take a look at another leap forward in our generational time a little bit. So here are some agents that are near to generation 50. And let's take a look at this one. Okay, he's able to scoop up the first piece of food, and it looks like turned around, avoided the wall. The first time it avoided the wall, the second time it looks like had some challenge. Notice when it's driving, it's doing this sort of shaky bit, and that's something that's also common in earlier generations where it's trying to find and focus in on the food and it does a little bit of shaking. So the spinning that I was talking about earlier also is a pretty common behavior for our earlier agents to try and find the food that they're looking for. So this agent, not too bad. Looks like at this generation able to scoop up 2 or 3. Okay, that was as I was saying, that was a dangerous thing to do, get to near the wall there. Our highly evolved agents were able to, let's check out this. So even when it had a little bit of distance, had enough time to turn around, wasn't quite able. And what that's showing is that our agents are not really adapted to avoiding the walls in a very sensitive way. They probably have just learned, well, stay away from the walls, so just don't get too close to them. And then when they get lured close to them by a piece of the food, they haven't yet adapted those dexterous behaviors to turn around rapidly and avoid running into the wall. Partly because they still haven't learned how to find the food, rapidly turn around and find that next piece of food to eat as well. One thing we'll find at these generations, because maybe a lot of our species are pretty successful at eating the food, the ones that are able to get into those dangerous situations and maybe skirt away from the wall when they can, they will avoid being penalized for dying. So let's see how this one does. Ooh, very good. As I was saying, we've now seen it sort of been replaced by ones that are much better at avoiding the walls. Why? Because most of the species are probably eating the same number of food. At some point, when you only have 700 ticks, if you're not really quickly scooping that food up in a really efficient way, there's only about so many pieces of food that you can do. And so running into the wall becomes a problem. Okay, let's take a look again at our most successful or our more successful ones right now. One thing you might notice is that, okay, this one's doing a little bit of a shake, but it's not shaking as much as those other ones, and they're driving at a faster and more deliberate speed than the other ones. And this is something that is also going to be favored. Oh, we got a wall collision. This is also something that is favored in later generations, is, because if we're already optimized to be scooping up that food and we're optimized maybe to not be running into that wall most of the time, then we're probably going to also now be sensitive to how fast we're eating that food. So anyone that's able to get that one extra pellet of food in the time, they're really benefiting their species, and they're being able to push evolution in that direction. So here at these past generation 200 here, well, I'm not sure what this one's doing. This is probably an example of a bad mutation. So this agent probably just mutated and unfortunately started spinning just a little bit too much, got too much output to one of its wheels, and now it's sort of stuck in a spin. Luckily, through fitness sharing, that agent is not necessarily going to bring down their species too much and might be filtered out in the next generation because of that bad mutation that it had. One last thing I thought I might just point out is that we do measure some of the data for our experiments as we're going, but largely also for debugging and making sure our algorithm is running well. And one of the things that we do gather is the amount of food that has been consumed each generation by all of the agents that we've got. And this, as you can see, this is a pretty standard, this is what we're looking for. We've got an increase of food as we're going, and we might expect that, right? The first ones were spinning around. A little bit later on, we saw them, they were starting to be able to at least eat that first piece of food, maybe before running off and crashing into the wall. And then finally, we see them improving and optimizing that over every generation. I've been running this for, as we've seen, over 200 generations, and that line is still going up, and it maybe looks like it's getting a little bit less steep there at the end. But I'm curious to see how long I can leave this before it starts to really peak. And that's an interesting thing to see. Now, on all of our settings, this is not always going to be true. I think I just got lucky with some good settings today, and maybe with a good batch. of agents in my initial batch. Now, the other thing we measure is how much time they spend out of time, or out of bounds, sorry. And this is not looking as good as that last graph up there. So, and maybe we saw why. And even in this generation, we saw that some of the agents still go and crash out of bounds. Now, this is how many ticks or time steps they spend out of bounds. So we can see these numbers here that 700 is how many ticks is one generation for one agent. So the number right now is at about 4,900. That means, well, if we think about that, the 7 full lifespans for agents, it's unlikely that any agent spending its full lifespan out of bounds or dead, but we expect that this is probably just a small group of agents that are still crashing every once in a while for different reasons. Well, here we are at almost generation 300 now, and whoa, that one's a pretty speedy one. They're still doing quite well, and let's check on, see if they're still improving their food consumption here, and it looks like it's still kind of going up. Maybe it's not quite as steep, maybe this curve is sort of curving itself down here. There's definitely a little drawback there, but it's still going. Now, my students, when they usually run these simulation runs, they usually run them for 400 generations. So I think I'm going to just hang out and see what happens for another 100 generations. All right, so here we are at generation 400. Again, we see some really well-adapted agents. Well, okay, that one's having a little problem picking up the food. But they all drive quite rapidly. And one thing we might notice here, we have a lot of extra data, but one piece of data here is we actually plot the average wheel output for all of our agents over each generation. So it's not, telling us about any specific agent, but more about the whole population. And we can see this sort of trend to go up, that they basically are trying to put full speed on both of their wheels as fast as possible so that they can rapidly go and pick up the food as much as they would like. One thing we might also see if we look into this just a little bit more is that the right wheel output kind of got to the maximum considerably earlier than the left wheel output. And one thing that we might see here is that a lot of our agents are going to be turning only in one direction. Well, of course, this one had to die on me. But I noticed earlier that if they needed to turn, let's see, so that one was turning right. Let's see if it ever turns left. So it turns right. See how it spins all the way around? Instead of turning left, it spins all the way around to turn right. And this is just because maybe the way the networks are adapted, or maybe the way the control systems are, they've decided, like, let's just put one of our wheels on full blast and we'll use the other one more to control where we're going. And that means I can only turn in one direction, or at least that's how I'm interpreting that particular behavior. It doesn't, so that one's sort of jittery, like it maybe wanted to turn left, but it seems like they're all turning right. In this behavior. Again, so that's something they could optimize out, but the question is there going to be a good evolutionary path towards that, or is turning right going to forever be one of the traits of the agents in our simulation? So again, at level 4, or at generation 400, let's see how we're doing on our food per generation. And we can definitely see there's now a slope sort of change. We're curving down. There's probably some asymptote we're approaching, or at least we're going to slow down more as we go forward. But it is still seemingly climbing at generation 400. An interesting thing now is maybe it's harder to optimize, food per tick. I have seen some really interesting runs where agents, both from luck of the random draw, but also just good driving, they've been able to eat 6, 7, 8 pieces of food in one run. We see here that the number of ticks out of bounds is actually, or dead, is actually going down. We do see a trend. At first I said there wasn't really a trend, but now we can see that they optimized that down a bit. We still get some outliers, but it looks like that might be something that's they're more able to optimize now that impacts their fitness in a way that allows them to keep going. So that they're both improving the food they're eating, and it looks like some steady decreasing of the time they spend dead to help improve that fitness. And we actually do plot the fitness as its entire both of those two combined with their weights involved. Now the numbers over here, of course, are just there are no units attached to them anymore. But in this particular graph, we still see that upward trend. So I'm going to keep watching this for a little bit while longer. But that's all I'm going to say for this video. So thanks a lot for watching, and we'll see you in that next video.